Welcome to lecture 7 in our series, and today is the big day. We're finally going to quantize a field. So after this, 12 hours of videos already, we have built a big set of tools. We apply those tools to quantum mechanics, mostly harmonic oscillators, but now we're ready to go into fields. And we're starting with the simplest kind of field, right? In terms of, remember, we're classifying our fields in terms of representations of the Lorentz group, and the simplest one is the scalar field, the one that does not transform under Lorentz transformations. The references for this lecture are the ones I like the most: is Peskin section 5.1 and Nastasi section 3. And to start, we'll quantize the scalar field in a canonical way. So we'll use the language of operators and impose commutation relations to the generalized coordinates of the system. So let's get down to it. Let's start by defining our scalar field phi, which is a function of defining every point in space and time, right? And write a Lagrangian for it. So the Lagrangian, I'll use more properly the Lagrangian density, but as I said before, I won't be insisting on the distinction, right? Will be this one. So half of del mu phi minus m square over 2 phi square minus what I'll call potentials. That has every other possible term you can imagine for phi, right? There's a lot of hidden assumptions here, right? So the first one, let's spend some minutes trying to understand this Lagrangian, right? Or at least convince you it's the appropriate one for us to work right now. So the first one is Lorentz invariance, right? And since phi does not transform under Lorentz transformations, it's easy to see that this is invariant. Any power of phi is invariant, and when I do derivatives in phi, all I have to do is contract the Lorentz indexes in the derivatives, and I'll have invariant objects under Lorentz transformations. And the second one is what we call degrees of freedom in quantum field theory, which is 1 in this case. I'm assuming there's only one scalar field and nothing else. This is not really a degree of freedom as you define it in classical mechanics, and we'll see that in terms of what you call a degree of freedom in classical mechanics, I actually have an infinite number of degrees of freedom here. But in quantum field theory, this is 1 degree of freedom. That's just setting up the language, right? And more importantly, there are some assumptions in this Lagrangian which are related to other symmetries. In particular, you see there's no odd powers of phi, right? They're not here explicitly. You could think, oh, they are hidden in here. But even for most cases, I'll assume they are not here either, right? And this is to keep my potential, right? We call this term the potential. Again, it's not the same as a potential as you would think about in quantum mechanics, for instance, right? But it's related to it. And I want to keep this potential bounded from below. So I don't want it to go to infinite values, negative values, for infinite negative values of phi. And keeping it only even powers of phi or derivatives, I can keep that. So essentially I'm assuming the Lagrangian is invariant under this discrete transformation that gets rid of the odd terms in phi. Right, this is implicit. I'll make exceptions to that eventually, and then the exceptions will be hidden in here. Another thing that you should pay attention and don't take it for granted, right? Because it's a common mistake that makes it very hard later to understand renormalization, right? Is these coefficients here, right? So even in here, I have hidden coefficients, right? Because I could, in principle, say have a phi to the 4th term here, phi to the 6th, and so on, right? And each one of these terms would have a numeric coefficient in front. And these coefficients are being written in very specific way here, right? It's ym squared over 2, y 1/2, y all of that, right? It's totally arbitrary at this point. Of course, it's not by chance. I'm not just choosing any random value. But keep in mind that if I would be rigorous and talk only about symmetries, I would really have something like that would look like this, right? And so on, right? C phi to the 4th, d, right? Phi to the 6th, and you go, and right? And these parameters, right? They're not set by symmetry. That the Lorentz invariance is here. I'm assuming these are just numbers, right? And eventually, I'll have to define observables for this theory. I would have to define what's the energy spectrum, what is how is momentum distributed, how is charge. Suppose there's charge here, we don't even know at this point, right? Because we don't know how particles will arise out of this, right? When I write little m, it's almost intuitive. I mean, it's almost reflexive for you to assume that's the mass of some particle, right? Has the right dimensions for mass if you do dimensional analysis here, and I'll get to that, but keep in mind that this is really what you can say at this point, right? You can actually do a little better than this, because the Lagrangian is not defined. You see, all you do with the Lagrangian is plugging into some action, right? And that is defined minus some normalization, right? So I can normalize this to whatever number I want. I can normalize it to 1, right? Or 1/2, right? Which is what I did here, just by changing phi. Remember, I can put this phi inside of a path integral, and this will be just a variable of integration. You can redefine it, right? Or even in the canonical formalism, I can define an operator minus a normalization, right? So I can throw this a over here, some power of a's, right? And effectively change these parameters to b prime, c prime, d prime, right? And have these terms in the Lagrangian, they're all operators. We call them operators, right? In practice, I have, if I set my Lagrangian to a finite number of operators, I'll have the number of operators minus 1 coefficients. They are free, right? They are free. And how do I fix these coefficients? I have to define observables and then compare these observables with experiment. That's what will tell me this is the mass, right? That actually the mass is proportional to b, right? Square root of b times 2, right? And that's the mass. So I'm already writing it in a way that in the end this will be the mass of some particle at 3 level, and that's the main point, right? So I'll define what 3 level is later, but the point is that the comparison of these coefficients with physical quantities is not trivial, and it depends a lot on the approximations you do in your system. We'll do almost everything in the course in a perturbative expansion, and then the comparison changes order by order in that expansion. Or it needs to change in a way that it's under control for the approximation, right? But it changes. So that makes, if you keep that in mind at all times, is a very important point. If you keep that in mind at all times, it will be easier to understand once you start going to the next order in the approximations, which will only come in quantum field theory 2, right? So a long way from now, right? You understand why this can be the mass now but not the mass later, because there will be corrections to it. So keep that in mind. Those coefficients are free. I'm already writing them in a way that for now is totally ad hoc, right? Ad hoc, and will become justifiable later when I finally define the spectrum. Then I will be able to see why this 1/2 is convenient here, why minus m squared over 2 is also convenient, right, for the spectrum. And this division, why I separated these two operators from what I'm calling the potential will become clear pretty soon. That is just the quadratic part of the Lagrangian, is the part I know how to integrate as a Gaussian, right? So this is very similar, will become very similar pretty soon to the harmonic oscillator. Everything else is more complicated, is an anharmonic oscillator, and we'll have to treat that with more care. So I want to make the separation, but this separation is just between the easy part and the hard part, right? That's essentially what I'm doing here. So that sets up the Lagrangian. Let's see now how we go about quantizing it. We want to do canonical quantization first, and that means finding the Poisson brackets of the theory and exchanging those Poisson brackets by commutators, right? And these Poisson brackets are between the canonical coordinates and their conjugate momenta. But what are the coordinates in a continuous system? Well, that is hard, right? So what we'll do is discretize the system first, right? So the first thing we do is to take space, and that's important. We're discretizing only the space coordinates. We're keeping time continuous. Right? Why? Because in classical mechanics, time is continuous, and that's no problem, right? Every coordinate is defined as a function of time, and we know how to do that, right? So we'll discretize only space. So I'm taking x, y, and z and dividing it into small cubes, right? And in each one of those cubes, I take the value of the field in some position on the cube, say the center. Doesn't matter because we'll eventually take the volume of those cubes to 0 and go back to the continuum, right? And my canonical coordinates will be qy, that depends on time, and I'll define these coordinates as square root of the volume times the value of the field inside that point. And I here is an index that is going through all the three-dimensional space in any order you prefer, right? I'm not using 3 indexes for x, y, and z because that's redundant, right? I can just use one, but I'm covering all three-dimensional space. This square root of the volume here, it's just convenience. I mean, it makes so I don't have to fix dimensions later when I go back to the continuum, right? But this definition is totally arbitrary, right? It's just convenient. And of course, this is, just to make clear, defined as delta v phi of xi t. So I'm running over the positions and assigning one coordinate for each. And this is where it's clear that I have, in viewing it from this point, infinite number of degrees of freedom, right? The moment I go to the continuum, I have to define the field in an infinite number of points to actually know the state of the system, even classically, right? So actually one field is equivalent to an infinite number of degrees of freedom. But we'll call just one field 1 degree of freedom at this in this language, right? In the field theory language. I also have to define conjugate momenta, right? And these will be defined in terms of the density of conjugate momenta that are defined a few lectures ago, right? That is defined in terms of derivatives of the Lagrangian in terms to phi dot, in relation to phi dot. And that again is just the value at some point, right? So for each of these cubes, I have a field, I have a momentum conjugate to the field, and I'm making those two the canonical variables of my system. Right? I also have to write a dictionary between the discrete and the continuum for the derivative. Right? So in terms of the derivatives, in the discrete version I have partial derivatives, so I can take any function of the fields or momentum or momenta and differentiate, say, in relation to the field, right? And these, with that normalization, will be connected in the continuum limit, right? At the moment I take this to the continuum, these values become a function in three-dimensional space, right? And so this becomes a functional derivative that I already defined, right? Oh, let me make this really explicit. So this guy can be a function of fields, which are then functions of space and time, and and these can be the field calculated at a different point, even a different time if I want, but let's make it equal time for now. And of course the volume is just between discrete and continuum. The volume is just d3x, right? This is very small volume, right? Which will become the measure of my integrals, right? So now the Poisson brackets, right? How do I write the Poisson brackets between these, any function of these coordinates, right? So take two functions, f and g, of those variables and calculate the Poisson brackets. This is defined as the sum over all the coordinates in the system, all the cubes, right, of del f, del qi, del g, del pi, minus del f, del pi, del g, del qi. Right? Now I want to know this in the continuum limit, because that's what I'll be using in what follows. Right? The first thing is to use these substitutions. Let me take my face out of the way. and use these substitutions here, right? So I'll get a square root of volume here, a square root of volume here, and then I can exchange these for the variables, the field variables. I'll have a 1 over delta v here. See, one square root of delta v and another one from these two, right? And I can write these like del f del phi I. Remember that index means I'm calculating at point xi. Del g del p gi, in this case I, minus del f del pi del g del phi I. Okay, so now I can do this trick, right? I can just multiply these by extra power of delta v over delta v square, right? And bring this delta v square in here, right? I take one power of delta v, put next to this guy, another one next to this guy, to use the definition of the derivatives. So that when I take the continuum limit of this derivative and this one, I get the functional derivatives for f in relation to phi and g in relation to pi, right? And I have a leftover delta v here that, together with this sum, becomes an integral in three-dimensional space. I'm summing over all the volumes, right? That means that in the continuum limit, right? I have infinite number of i's, volumes goes to 0. This part becomes just the integral in d3x. And all these derivatives inside become functional derivatives according to this dictionary, right? So they are just del f, delta f, delta phi, delta g, delta pi, minus delta f, delta pi, delta g, delta phi. And that's the definition of my Poisson bracket in continuous, in the continuous version that I'll use for fields all the time. Right now I have functions of those fields, right, and derivatives of the fields, all good, still classical field theory, right, but very convenient way of using for quantization. The main Poisson bracket I'm interested in is, of course, the Poisson bracket between the coordinate and its conjugate momentum, right, which is this one, between phi of x t and pi of x prime t, right? Notice we're doing this Poisson bracket at equal times. I'm changing the position, but I'm keeping time the same. And for now, it's just that we have to take baby steps here, or we'll get lost, right? So I'm just following what we do in classical, doing what we do to quantize classical discrete systems, right? And when we do, we actually impose commutation relations between equal time variables. So for now, it's just simplifying stuff. If I do in the same way, I do it in the same way and keep equal time for now. Later we'll go back to see how the commutator between the fields can look at different times when we discuss the causality of these theories, but that will come down the line. For now, it's sufficient to say that the commutations relations we'll get this way are covariant, so they are valid in any frame of reference that you choose once you impose them in one of them, right? So this just using this definition for the Poisson brackets in the continuum limit is very easy to calculate. I have some integral in space. I'll use this variable y here, right? And I have delta phi of x t in relation to phi of y t times delta pi of x prime t in relation to delta pi of y t. This just from the definition here. The second part is just 0 because I'll have delta phi in relation to pi and pi in relation to phi. This is all 0 because these functions are independent from each other. And these, just remember the definition of the functional derivatives that I defined a few lectures ago. This is just the Dirac delta in 3 dimensions of y between I, y, and x. And this one is the same between y and x prime. X prime, right? And of course, then I can use this integral in y to get rid of one of those deltas, and I'm left over with the other delta. So this ends up being just delta 3 between x and x prime. right? That's the Poisson bracket between phi and pi. The other Poisson brackets are really easy to calculate. So if you do phi, there will be 0 because either one of those derivatives is always 0, right? Same for pi. Let me just be careful with the notation. This is the Poisson bracket because later we use the same symbol for anti-commutators, Poisson bracket. This is just 0, right? And those are the equal time relations. And now I quantize it. Quantizing in this case is just in the canonical formalism, right? I use this dictionary. I exchange Poisson brackets by minus I. If I'm not doing natural units, there's a H bar here, but mostly I'll just ignore it, times the commutator. And the same will happen here. So I have the commutator at equal times equal to I delta 3x minus x prime, and phi xt phi x prime t equal pi x t pi x prime t equal 0. Right? And these are the equal time commutation relations. Right? So that quantizes the theory. Now we need to see the consequences of this. But in order to do that, we have to understand a little better what kind of system are we dealing with. And that involves going back and forward between the classical and the quantum theory to give us a better intuition. So the first thing to notice is what happens in the simplest case, which is when I take that potential to 0, right? I just take that potential that I wrote in the Lagrangian, right, up here, this one, to 0, just to see what happens in this case. So now V of phi del mu phi is just 0. That means my Lagrangian is just half del mu phi minus m squared over 2 phi squared, right? And this is what we call free scalar field. Free scalar field, right? Because we are turning off that potential right there in the Lagrangian. And it is, of course, the simplest case, right? I can, in the conventions we're using, which my metric is plus, minus, 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 right? We can rewrite this as half the part with the time derivatives minus half the space derivatives minus m squared over 2 phi squared, and use the principle of the extreme action to see I'm going back to the classical theory here to take a look, right? So I can write the classical solutions, the classical configurations of the field. Now the solutions of my equations are not time evolutions of these variables, but the whole a whole set of configurations, right? Evolving in time, but also in space. I have phi defined for all points in space and time. So each solution is actually a configuration of phi in space and also the evolution in time. Right? So for that I use, of course, the extreme action, which gives me this equation, right? That I have shown before for the Lagrangian density. And if I just use this here, the derivatives in phi act here. I have a factor 2 that goes away. Then the derivatives in del mu phi, it's easier to look here, right? There will be del mu minus del mu phi. And this is equal to 0. Which of course I can just reorganize. There's a global minus here that goes away, and I can write this as del mu plus m squared acting on phi, and this is 0, right? Remember that this del mu phi I can write again as del t2 minus the space derivatives, which is the Lambertian operator, and this is just, right, that means del mu is just this, and this means that equation is just this equation, which is Klein-Gordon equation. Klein-Gordon equation. Right. So now we at least have a very good clue to what we're dealing with here. At least in the simplest case, which is the potential going to 0. This is just the Lagrangian that gives you the Klein-Gordon equation. I mentioned that before, right? One way to get to this Klein-Gordon equation would be to go through all that very problematic relativistic quantum mechanics path, right? You quantize wave functions, and then you try to you quantize position and momentum. Then you try to quantize the wave functions again, second quantization and all, to get here. Now we got in a very clean way, right? I'm doing a field theory. My variables are fields, and I just choose the Lagrangian that got me the Klein-Gordon equation. And how did I choose that Lagrangian? I just took the simplest field possible, that is a scalar and the Lorentz transformation, right? Of course, there's some extra stuff. As I said before, these coefficients, half and minus m squared over half, if they had, I don't know, if I put 1 here and a half here, the relation would be wrong, right? But then it's just a change of variables to see that it's a Klein-Gordon equation. So I'm starting with variables here that are very convenient. But other than that, I'm dealing with a system that is described in the free limit to the Klein-Gordon equation. That means if I find solutions in this limit, then I can later put this potential perturbatively, right? And it will become pretty soon why I have to do that. I cannot do it exactly, right? I have to do it perturbatively. So now to get even more information out of this, let's go to momentum space, right? Let's do a Fourier transform for this field. So I'll take phi of x and t, and do the Fourier transform. So write these as functions of the momentum conjugate to these positions, right? 2 pi the cube exponential of I x p phi. So now I'm defining a different function. Should call it phi tilde, right? But I'm lazy. I'm not putting the tilde. But remember, this function is not the same as this one, right? And the variables indicate what function I'm talking about, just to avoid carrying this tilde all the time, right? I can invert this relation. Okay, all fine and cool, but I have to be careful about a few things here, right? So I didn't say it before, but I need the Lagrangian density to be a real number, right? That means these guys are real. They're not complex numbers, phi, right? Otherwise, I would have to have a module here, right? And that means that in order for this guy to be real, since I'm shoving complex numbers in the middle here, in order for these guys to be real, these guys must be complex, right? And speaking, of course, I'll make these guys, as I said, I'm going back and forth between fields and operators, right? Or classical and quantum, right? Because in this case, once I impose the commutation relations here, these guys become operators. Yeah? What I need to happen here in order for this guy to be real, it means the operator will have to be phi dagger needs to be equal to phi. That will imply, in order for this to be true, this guy will have to be have a different property, and phi dagger of pt will have to be different from phi, and in fact it needs to be equal to phi of minus pt. That's easy to see, right? If I take the dagger here, I change the sign in the exponential, right? And I take the dagger of this guy. If then I can write it like this, I'll change the sign of p, and then it's just a change of variables in the integral to change the sign of p everywhere, right? And then I get to the, I mean, it's easy to prove. That's a good exercise. You can prove that if this is true, then this guy is real, right? If you write not in, this is written in the operator language, but if you write in the field language, just exchange dagger by the complex conjugate. It's the same, right? And you can prove that. So this needs to be true. And this is a very similar situation for pi, right? I can also define pi of xt as 2 pi to the cube exponential I x p. Pi again should be tilde, but I'm lazy. P t, and the same, right? The same relation needs to be true for this pi. It needs to be a complex function and to keep this guy real. With those definitions, I can go back and write this equation in momentum space. Right? I can go and write this in momentum space. Just recall that when I act with the space derivatives on the exponential, right, I essentially get powers of IP down, right? So that will be minus modulus of p square exponential of I x p. So if I come in here and exchange phi by this expression, right, I'll get this operator acting on this exponential, right? The time derivative does not act directly on this guy, but the space derivative acts on the exponential. And I'll get these powers. Right? That means my equation will become, let me try to write down here, will become just the integral in d3p over 2 pi to the cube. This is coming from exchanging phi by this expression. So this integral goes here, goes all the way outside. The time derivative I leave here. Then I have minus this, right? But that I can exchange by plus p square, which is because this derivative acted on the exponential, plus m square phi of, oh, exponential, sorry, the exponential of I x p acting on phi of p t, and this is all equal to 0, right? I just substituted this in here and acted with the space derivatives on the exponential that was here, right? So I essentially exchange the space derivatives in this way. Now I can further integrate this in space. So I can take the integral of exponential of minus I x some p prime. This is just to simplify things, and since there's nothing here that depends on x other than this exponential, this becomes just the Dirac delta of p prime and p, which allows me to make this integral in p and write, and then I mean the integral in p will make everything here be written in terms of p prime, but then I just drop the prime, right? So I get the following equation. Let me put this in white. This becomes del 2 del t2 plus, it would be p prime, but I'm dropping the prime in the end, plus m square phi of p t equal to 0, right? Which is what we call the Klein-Gordon equation in momentum space. So Klein-Gordon in momentum space, right? Klein-Gordon in momentum space, right? And just to make things clear, right? We know how to solve this equation, right? Solutions to this equation, now it's easy. It's just time derivatives, right? It's just some constant f of p, of momenta only, right? Exponential of plus, minus, I mean, there are solutions with plus, there are solutions with minus, I omega t, right? You just have to substitute this here, right? And then, of course, the time derivatives bring down powers of I minus or plus I omega, right? And you get plus minus I omega square plus p square plus m square f of P equals 0, right? And this is for, if you want this to be true for generic f of P, that means that omega square, which I'll call omega P squared, just to remember, is a function of this momentum, needs to be, I'm defining these as P square plus M square, right? Which are frequencies, right? So what we're finding is that the solutions of the Klein-Gordon equation look like harmonic oscillators, free harmonic oscillators. That's why, and not forced ones, right? That's why I'm calling free scalar field. And with frequencies that are given by this relation, right? These are the natural frequencies of those oscillators. So why is this useful to us? Why noticing this? And remember, we are in the case where the potential is 0. So the simplest of the simplest cases, right? And why is this useful? Because we're quantizing this, right? We already know the commutation relations we want to impose. But if this is similar to the harmonic oscillator, then it might be very useful to do the quantization in a way which is also similar to how we quantize the harmonic oscillator. This will be perfectly good when the potential is 0, and maybe even useful when it is not 0. We'll see, right? And what do I mean by that? That means exchanging my canonical coordinates, which now are phi and pi, by a and a dagger, those ladder operators. So we'll do that, right, with the proper normalization. So now I'll define these two guys. Let me get my colors for definition. Is A of kt will be defined as square root of omega k over 2 phi kt plus I k pi of kt, which is exactly the same as I did with q and p before, right? So, but now it's phi and pi. Of course, this guy is a field, right? This is also a field, right? And a dagger is, of course, the dagger of that. Amazing how that works, right? Omega k over 2 phi dagger k t minus I square root of 2 omega k pi dagger k t. Right? So these are the definitions of A and A dagger. So now I follow with my harmonic oscillator algorithm, right? I now have to go and use the commutation relations I define for pi and phi, and get commutation relations for A and A dagger, right? That's essentially what I need to do. But first I need to invert this relation. And note one thing, we have to be paying attention that the omega only depends on the modulus of p, right? So every time I say omega k, it's just omega of modulus of k, right? That will be important when we're doing integrals. This guy does not actually depend on the direction of this momentum, which is important for us. Just inverting these relations, what I get is that phi of x t is equal to the integral d3p 2 pi cube 1 over the square root of 2 omega p a of p and t exponential of I p x plus a dagger of p t exponential of minus e p x. I just inverted the relations here, and that's substituted in the definition of phi of x and t at the start, right, in terms of phi of k and t. Right, now you can see that phi of k, if I take the dagger, I have to invert the signal of the momentum, right, because this is essentially phi of k. Now, remembering this fact here, we can actually do a change in one of the integrals, right? I have an integral of d3p over this first part, and then an integral of d3p over the second part. And on the second part, what I can do is just change the sign of p in this way, right? I can take d3p or omega p a dagger p t, and it's actually the square root of omega p, but that's fine, it's the same. Exponential of minus e p x, right, and do the following changes. So I just take p to minus p, right, and omega p that shows up here, I put square root of omega p, right? Omega p that shows here stays the same because of this, right? So this guy does not depend on the direction of p. That change of variables will invert the extremes in all the integrals. So these integrals are from minus infinity to plus infinity. They all become infinity to minus infinity, all three of them. All right, let me write it. There are limits to laziness, right? So let's write all the integrals. This becomes minus d3p, the square root is the same, and of course a dagger becomes a dagger of minus p t exponential of I p x. Right? That means if I go, and then I can invert all these three integrals, just flip the limits. This will result on a total minus sign. Right? If I take all these minus out of here and put them here, this will be a total minus sign because I'm inverting three integrals, which conceals this one. So I end up with the same thing that I had here, right? But the exponential changed to become equal to this one. So now I can put the exponential outside these brackets here, but I have to change the sign of p in the a dagger part, right? That means I can rewrite phi of x in this way. This is all the same. This I'll just as I have shown here, I can put a minus here and change this to positive, and that means I can take this exponential outside and then organize stuff. I make a proper plus. A dagger goes here, the exponential comes over here. I can do the same for pi, right? It's actually the same calculation, right? And write that pi of x t is equal to the integral in d3p 2 pi to the cube minus I omega p over 2 exponential of I p x of a p t minus a dagger of minus p and t. It's the same as here. Just put this in here too, so it looks more symmetrical. Right? And now this is very convenient because I know the commutation relations between phi and pi. I have to put these two definitions in there and solve for the commutation relations for A and A dagger, right? In momentum space, right? I won't do that here. It's a good exercise. You can either do it or just check the answer, which is pt a dagger of p prime t is equal to 2 pi to the cube delta Dirac of p minus p prime, and every other relation is just equal to 0. So A with A is equal to A dagger with A dagger, and both are 0, right? As expected, right? This is becoming so similar with the harmonic oscillator, right? It almost justifies all the time we spent at the harmonic oscillator in our life. Right? So you can check these relations, either do it in this direction or the opposite direction, it doesn't matter. Try to do it first, but then if you don't, if you get stuck on something, that's on my lecture notes. I do it in details there. Okay? So you can go there and look if you get stuck. Right? And now, using those two definitions, we can go back to the Hamiltonian operator for this system, right? So now, again, going a little bit back to the classical field theory, we have seen that you can define the Hamiltonian of the system in terms of the the Hamiltonian density, right? Which is just pi of xt phi dot of xt minus the Lagrangian, right? So this is what we called this nice h here, which is the Hamiltonian density, right? Now, if I figure out who pi is for this system, right? Pi of xt is just delta Lagrangian delta phi dot, right? If I look back to my Lagrangian, remember I'm still thinking of the case where the potential is not there, right? So this is just del phi dot of half phi dot square plus other things that do not depend on phi dot. Right, well, that's a very bad plus, right? So, which means the derivative is just a phi dot of x and t. And that means my Hamiltonian of x t, keep forgetting that, right, is just half of pi square plus half of the space derivatives plus m squared over 2 phi squared, right? I just substituted the definition of the Lagrangian here and subtracted, right? That's all. Now I want to use these definitions, these two, in here in order to write my Hamiltonian in terms of A and A dagger, right? The same thing we do with the harmonic oscillator, right? It's all, I mean, the same same procedure. This is a straightforward but lengthy calculation, so I'll go over it a bit faster, and I mean, really, you should try to do it yourself and look at the video or the lecture notes only if you get stuck somewhere, right? So I want to take this Hamiltonian here, so this is the integral of the Hamiltonian, and in place of the Hamiltonian density here, I'll replace this expression. So I always have a quadratic term on these phi's and pi's, and I'm substituting phi and pi by their definitions up here, which always involves Fourier transform, right? This integral in momentum, and that's why I get these two integrals here for p and p prime, right? So this is just the term that comes from pi square, so I'm just using the definition above, this a dagger pi square, right? Get this exponential here. This is the term for the space derivatives acting on phi, right? Of course, once I write phi in terms of the Fourier transform, these space derivatives, see, nothing here depends on the position, only the exponentials that come, that were here, right? So the space derivatives will act on them and drop powers of IP. In one case IP, in the other case IP prime, and that's why you get this minus P times P prime over here. And finally there's the term with phi square, which is just writing this big expression. Notice that after, there's two things here, right? One is that after I act with the space derivatives, I drop these powers, but then the exponential that is left is the same that I have here, which is the same that I have here. So all these three exponentials I can put outside these big brackets here, and I have just one exponential factor, which is overall to everything. Also, these terms with A and A dagger are the same here and here. They are different for the pi square term, but for the terms that involve phi square, they are the same, right? It's the same in both places. That allows me to simplify this expression to this one, right? So I brought the exponential outside, as I said. Now the exponential is common to everything, and I have these two types of multiplications between A's and A daggers, of P's and P primes, right? So I gain a factor 2 here, and that's why you don't see this half. It's gone, right? You basically just grouped everything together. And then what I will use here is that since nothing here depends on position anymore, right? There's no x dependency here. I can do the integral in x. This is just a Dirac delta, right? This 2 pi to the cube kills one of these 2 pi to the cubes that I have here, right? There's a cancellation. And then I can use this Dirac delta to integrate either in P or in P prime. I choose P prime, so I'll do the integral in P prime up here. right? And the effect of that, right, is just exchanging everywhere else p prime by minus p, right? So I'm getting rid essentially of 6 integrals here. I'm doing all the integrals in the position and all the integrals in p prime. In these coefficients here, the consequence of that change will be, we know that omega does not depend on the direction of p. So if I take p prime to minus p, these two omegas become the same, and that's what you get. Here, this p scalar p prime will just become modulus of p squared, and the minus go away with the minus that is coming from here. And the omegas in the denominator will become the same too. You get this, right? This on the numerator is also the definition of omega square, and so you get omega over 4, right? Which means both these and these become proportional to omega to the 4, which I can put ahead and add up these two parts, right? I need to do some simplification here. This is just pure algebra, right? Just multiplication. And then you see that the cross terms go away. The terms that have dagger or AA, which are here and here, they go away because there's a minus sign between 1 and 2 up here, right? This is proportional to minus omega over 4. This is proportional to plus omega over 4. So the terms that are equal here go away, and you have only these terms that involve AA dagger or A dagger A. So putting it all back here, I get the simple expression for the Hamiltonian, right? Which is, again, apart from this integral, the same as the harmonic oscillator for frequency p. But now I have an integral over all frequencies, right? For overall p, right? Which will mean changing frequencies. The Hamiltonian of the system really looks like a bunch, an infinite number, a continuous infinite number of harmonic oscillators, right? You see, for each value, fixed value of p, you have a harmonic oscillator Hamiltonian here, and I'm varying p continuously and adding up over all of these, right? This is the first important thing to notice here. We can improve a little bit how we write the field phi in terms of A and A dagger. If we think just a little bit about how the time evolution of A and A dagger is, right? We know that the time evolution of any operator is given by its commutator with the Hamiltonian, right? And this commutator is easy to figure out, right? Just plugging a commutator here and see the commutation with A and dagger. That's easy to do. Also, you can find it in the lecture notes, and you get just omega p A of p t. And this equation, that the time derivative of A is equal to omega A, right, it's also easy to solve, right? We know that this is just A p t is equal to some operator that now only depends on p, not on time, right? Some coefficient, but in this case it is an operator. Actually, just to be clear, I'm suppressing this operator notation because I keep going back and forth between the quantum and the classical theory, but it should be obvious, and I'm never commuting stuff even when I can, so I hope there's no confusion being created by that. So mostly we're talking about operators, and so the solution to this equation here is just a exponential of minus e omega p t, right? And you can do the same for a dagger, right? A similar equation, the commutator of a dagger with Hamiltonian, and get a dagger p t is equal to a dagger of p exponential of I omega pt, right? The expected time evolution for operators, right? And then I can take these two expressions and go back to the definition of the field in terms of an a dagger, which I have somewhere up here. Where is it? This one, right? Let me copy it. And put these two expressions here, right? What I'll get is that I use the minus p1. Actually, remember, I can distribute this exponential in here, put it here, and put it over here. But then I know that I can do this, right? By changing the sign. The sign does not change here because the sign change in this part is compensated by the integral limits, and this does not change. So I can write it like that, right? And now I use these two expressions. So this guy is substituted by this. And this one, a dagger, is substituted by this. Right? And now I can put these exponentials together, right? By with the provision, right, that the zero component of the momentum vector, or I mean the energy, I'll call this EP, is equal to omega p, right? Which is kind of fine because omega p is the square root of p squared m squared. But remember, that's an important point. This is kind of surprise at this point because m was just some coefficient that I put in my Lagrangian. There's no particles here yet, or at least I still didn't identify particles. But you see things that remind us of particles showing up, right? The energy of these harmonic oscillators is connected to these momenta by a relation which is very similar. I mean, is very well known to us, right? This is an important thing. But given that I'm assuming P0, I'm naming P0 after this omega, right? Then I can write this phi of x t as the integral in three momenta. Now I'm calling this EP, A of P, which is a thing that does not depend on time anymore. Right? Exponential of minus EPX plus A dagger. And now I'm suppressing the arrows here. That means this is a P mu. It's like this is the scalar product in 4 dimensions, right? In Minkowski space. P exponential of plus IPX. Right? It's the opposite sign of that other exponential. Right? remembering with the provision that P0 is equal EP, which then is omega P, or I'm just changing language a bit here, but it's the same variable. So this is a very convenient way of writing the field, because we're going in the direction of writing it in a totally relativistic, friendly way, right? So already we have products of form position and for momenta here. Still the integral is only on 3 momenta, but we can fix that. You'll see that we'll fix that later. Okay? And I won't do the same for the conjugate momentum, but it's easy, right? We know that the conjugate momentum x and t, in this case, right, for this Lagrangian, is just phi dot, so I just have to do the derivative in time there, and I'll get pi, right? Written also in terms of these exponentials. Right, 40 powers of P0 in front. So far so good, but now we need to worry about the states, right? We've been dealing with the operators of this theory, but we have to construct the Hilbert space of the states of the theory, right? Choose some operator, find eigenvectors, and build a space. And again, to do that, we will resort to discretization, right? Because everything gets a little less difficult if you go to some kind of discretization. But this time, instead of discretizing space, which is what we did before, now we do something that is a bit more physical, which is assume we are in a finite space, right? So what we did before, we took the field phi of x and t and wrote it as a Fourier transform. That means I'm decomposing it in its Fourier components, right? Modes of vibration of that field. And let's assume now this field lives in a box, and I have some boundary conditions which tell me the field needs to be 0 at the boundaries. That means not all modes will be possible now, right? We know that if a space, let's say in the z direction, right, is finite, I'll have modes of oscillation, k, z, n, which are integer multiples of 2 pi over the length in that direction, right? So when I put this field living in a closed space, what I do is that I discretize these modes. I discretize these momenta, which is the modes, the Fourier modes of the field, in which I'm decomposing phi x t, right? That means that I'll change in the previous expressions, right? I'll exchange the integrals in d3k or d3p by 1 over v sum over these modes, right? So over n or over k zn. Let me put a proper z here, right? Kzn. This 1 over v is because in natural units, momenta has dimension of 1 over distances, right? So the proper dimension is 1 over v here, right? And the Dirac deltas in in momentum will be v delta k prime, right? Okay, so also I'll use the following definition in the discretized limit that takes care again of all the dimensions and other convenient factors, right? For the ladder operators A and A dagger, I'll write them in terms of alpha and alpha dagger. So do not confuse this alpha with something else, right? In here, alpha is just the same as the ladder operator, but in the discretized limit, and that's why it's convenient to have these factors in front. In fact, with these factors, we have that this relation, which is the commutation relation for A and A dagger, which is usually, as is shown before, just 2 pi to the cube delta cube of k minus k prime, right, becomes, right, on this side I'll have a similar definition for A dagger, right? So I'll have this square will be just v 2 pi cube alpha k alpha dagger k prime, right? Just substituting these here and here. And on the right side, I use this definition, right? Again, this is obligatory because of the dimensions of the Dirac delta compared to the fact that the Kronecker delta has no dimensions, right? This is just 2 pi cube from here, and then I get this v delta Kronecker k prime, which then allows me to send all of these away, right, and get a commutation relation for alpha and alpha dagger, which is just the same as the harmonic oscillator, right? That's why I put these terms here, as to not be carrying around powers of pi or volumes, right? And that's the main objective behind it, right? Now I have to go back to the Hamiltonian I had up here. Let me copy it, this one, and discretize momenta, right? Because this is an integral in momenta, and now it will become a sum, because not all momenta are possible. I just discretize the modes, the normal modes of the field. So this is the Hamiltonian, and I just have to substitute A dagger and do all those prescriptions, right? All the discretization dictionary that I wrote up there, right? So the integral in momenta just becomes 1 over v sum over k of 1 over 2 pi to the cube omega k over 2. All these a's and a daggers bring powers of square root of v 2 pi cube square, right, because there are 2 of them. So I just get v 2 pi cube here. Again, this goes away, right? And I get alpha dagger of k alpha k plus alpha k alpha dagger of k. In this case it's all the same k, which gives me a very familiar expression, which is just the sum over case of harmonic oscillators, right? As I had told you before, was pretty obvious actually, right? And this is just a sum of harmonic oscillators, and now by putting this field on a box, I made the continuous sum of oscillators become a discrete sum over oscillators, right? In fact, I can baptize these as H, like a little Hamiltonian of one oscillator K, and the full Hamiltonian is just a sum over these many small oscillators, right? And of course I can rewrite these, just use the commutation relation between these two guys and write H k as omega k n k, where n is alpha dagger alpha is the number operator. This is the number of excitations in any given oscillator, right? It's the number of excitations in that oscillator, and the frequency of each oscillator is omega k, right? And I'm summing over all possible frequencies. Now, the Fock space of these is pretty obvious, right? You have basically for each mode k, you have a state which is defined by the a set of states which are defined by the eigenvectors of this number operator, so nk, which counts how many excitations with frequency k I have. Right? And that's for all the frequencies. And everything else works as expected. Right? So you have these relations, which is what you expect from a harmonic oscillator. Right? So raising and lowering operators increase or decrease the modes. This is the energy of each of those oscillators. You define a vacuum by acting the lowering operator on 0 and so on and so forth. This is the normalization of the states, and this is the vacuum condition, right, in terms of the number operator. In the context of quantum field theories, we usually call this creation and annihilation operator. So the dagger one creates, the without dagger annihilates, because we'll call this n right here, right, the eigenvalue of the number operator as the number of particles. Now this is just a name, right? A extrapolation, an interpretation on my part. But next lecture, I'll show how far we can take this interpretation. Right? In order to call these particles, I have to prove that they have a lot of properties. So this, for instance, if I create a certain number of excitations, the momenta carried by each of the excitations need to be a number, a multiple of a center number, which relates to the energy also carried by this number of excitations in a way predictable, which is related to the mass, right? Momenta, energy need to be related to each other by the mass of the particle, by the relativistic dispersion relation. And suppose we have a charge in the theory. This number of excitations also need to carry a multiple of the charge, which is so that everything is consistent with one particle. So all these quantum numbers must behave as multiples of what you expect one particle to be, right? And that's what we start showing next lecture. We want to look at the spectra of these theories and see if we're really talking about particles. And also, I want you to keep in mind, I still didn't build the Hilbert space of this theory, right? I have kind of a multitude of Hilbert spaces right now. So for each of these discretized Hamiltonians here, for each of these oscillators, for a particular mode K, I have a Fock space on, which is a Hilbert space for the harmonic oscillator, right? But I still didn't build the space for the whole Hamiltonian. And that's one of the things we'll do next time, and show where the particle interpretation comes from, which it's quite a nice result. So I see you then.